final showcase on the 22nd of March 2021. Who would have believed nearly 1 year to the day of the initial lockdown that we would still be running virtual events? And as novel as that seemed at the time, it has, of course, become very normal today. There are quite clearly benefits to this virtual approach, not least the reductions in travel and the resulting benefit to the environment. And I'm sure many of you would have had to have traveled on a Sunday evening, stay overnight in a hotel, or get up very early for the train journey today. But personally, I do look forward to the time when we can meet face to face again. I suspect some of the most successful collaborations we've seen over recent years, and let's be honest, there are so many to choose from, were created over a coffee or even a beer, dare I say it, after an industry event. Imagine that. Well, it does look like that might not be too far away again, with any luck. It's great to see so many familiar names on the registration list. It's made me realize how far this industry has moved on since the initial series of collaborative research and development projects in the world of connectivity and automation. Thank you for your continued support. But also to those who are new to this, despite the enormous progress that has been made in the grand scheme of things, we really are still at the early stages of this research path. And I think it's worth mentioning the sustained support from the Centre for Connected and Autonomous Vehicles and Innovate UK that has been an integral piece of the jigsaw to ensure that UK companies and academic institutions can play a leading role in this global challenge in the UK. And that's exactly what the Catapult network is here to do, of course, to identify opportunities for innovative SMEs, industrial partners, and universities to grow and use the skills in our organization to facilitate those relationships and deliver world-leading projects. And VeriCAV is another fantastic example of exactly that vision. HORIBA MIRA leading an extremely complex research project with the University of Leeds, Aimsun, and the Connected Places Catapult. And that leads me on briefly to today's agenda. In a moment, I'm going to hand over to Annabelle Basford from CCAV, and that'll be followed by an overview of the project itself from Tim Edwards at HORIBA MIRA. And then we'll have a number of updates from colleagues at the University of Leeds, HORIBA MIRA, and CPC. So on behalf of the Connected Places Catapult, thank you, and I hope you have a thoroughly interesting and informative morning. Over to you, Annabelle. Thanks.
Thank you. I'm just going to share my screen so you can see my slides. Okay, can everybody see that?
Yes, we can see it.
I'm going to. Great, thank you for confirming. So my name's Annabelle, and I'm a project advisor at the Centre for Connected and Autonomous Vehicles. And in okay, can everybody? I'm going to quite close. And the DFD, that's the Department for Business, Energy and Industrial Strategy, and the Department for Transport. And while both of those departments, we do work cohesively as one team. So first and foremost, we're CCAV, and it doesn't make that much difference. And the aim of CCAV is to encourage research and development of connected and autonomous vehicles in the UK. Way. We also have part of the team who work on the future of transport, so not connected and autonomous vehicles, but other sort of future-facing innovative transport solutions. So, for example, they were recently doing some of the work around e-scooters. There are 3 CCAV pillars towards developing connected and autonomous vehicles safely and securely in the UK. So one is a clear regulatory pathway. So, for example, that includes things like the Code of Practice, which is around how to, the rules around testing an autonomous vehicle on UK roads. Secondly is joint investment in R&D, so that's joint government investment with industry and academic partners to do some really innovative and interesting things in developing CAVs. And thirdly is an integrated testbed ecosystem. So that is the work that Zemzic have supported, where we've got several testbeds throughout the UK, which allow a real variety for testing CAVs in a safe testbed situation.
Hi, Annabelle. Sorry to interrupt you. We've lost your slides. I think you might be having a little bit of connectivity trouble. Can you try resharing?
Yes, I will try to reshare. Can you see them now?
Yeah, we can see PowerPoint again. Thank you.
Perfect. Okay. Okay, hopefully that's still working. So I'll move on to the next one. I just talked through the 3 pillars. So the next slide is about the government being clear that it is committed to developing CAVs in the UK. And there are several reasons for that. So the government believes that CAVs have the potential to transform society and that there is a strong business case for them, meaning we think that there is an opportunity for money and investment to be brought into the UK through CAVs. And furthermore, it says here that there's a global race for supremacy. So I think by this we mean that there are opportunities within CAV development for the UK to be a global leader in certain areas, and simulation is one of those. Some key facts and statistics that we think CAVs will support us to improve on are that in the UK, cars are typically used only 3% of the time. If we were to move more towards mobility as a service in the future, that would mean that vehicles are being used more efficiently in the UK. Secondly, based on current trends, congestion will cost the UK 10 billion a year in lost time by 2040. We believe that CAVs developed the right way will be able to reduce congestion significantly, and so that would improve on that figure. Thirdly, human error is a factor in 95% of crashes. So if CAVs removed that human error from the equation and were proven to be safer and better at avoiding crashes than human drivers, then that would be a real benefit as well. And finally, the UK has an ageing population. As people age, mobility may become more difficult. They might not be able to drive themselves where they would like to go. So if CAVs were an option, that would hopefully mean that there's the opportunity for mobility longer into life, and that they can continue to get around where they would like to go. So the next slide is on how CCAV has supported the UK CAM ecosystem. So our innovation programme has jointly committed with industry more than 400 million through the ecosystem since 2015. The funding has contributed to the success of lots of companies within the CAV sector, and that includes some companies that have been involved in the VeriCAV project. So the examples on here are Latent Logic, Origo and Aimsun. We also believe that the UK is a really great place to do CAV testing and development because of the variety of roads, the variety of weather, the number of test beds that we have, and lots of other factors, which means that if you're developing CAVs in the UK and can show that they work in the UK, more than likely that will be transferable to other places in the world as well. And then on simulation specifically, we see simulation as a really important part of CAV development, and across the projects that we've funded, we've seen them using it in lots of different ways. So for example, using it to improve the engineering of CAVs, by which I mean using the simulation to identify areas where the CAV is not performing as well as would be liked, and then going back and improving based on that information. Secondly, to verify and validate CAVs, so to give that tick that they are performing safely and that they are doing everything that is claimed of them. And thirdly, to model CAV and mobility as a service. So for example, that could be plugging in loads of assumptions about human behaviours into a model and then seeing how they respond to different scenarios. So for example, a traditional taxi service versus a CAV taxi service. So those are examples that were already being used across many of the different projects we have. But in 2018, we ran a simulation and modelling competition specifically, so where simulation and modelling would be the focus of those projects. And as a result of that, we funded 5 R&D projects, VeriCAV being one of them. And the aim of that competition was to develop how simulation can support approval and standard mechanisms. And most of the projects were focused on verification and validation. I'm now just going to play a short video which Aimsun provided to us. It's from their work in the Human Drive project a couple of years ago. So you can see this is showing a model where on one side it's no autonomous vehicles, so all just normal driven cars. And on the other side, it's how that same road would look with autonomous vehicles driving on it. So you can see that in different scenarios, autonomous vehicles have less congestion. It also compares their performance and things like that. So this is one use case for simulation in our projects. So we're now turning to these CAV-Sim projects that we finished as they are coming to an end or are a significant way through their work. We now want to ask them about the role of simulation in the future and how simulation can continue to support CAV development in the UK. So CCAV have a small amount of funding for the next financial year, 21-22, but this is focused specifically on safety and security. Simulation has a significant role in safety and security, but with the small amount of funding, we don't think we'll be able to do any large R&D competitions. However, we are interested in your input to understand how simulation could support smaller, more focused scopes potentially. We are hoping for a larger multi-year spend in 2022-23 and onwards, and that would be an opportunity for more large collaborative R&D similar to the CAV-Sim 2018 competition. Or alternatively, it could be large collaborative R&D projects on different themes, but where simulation has a significant role and is a significant part of those themes. So we'd be really keen to hear thoughts on how simulation could be part of that picture in the future. So we've had a few conversations recently with the CAV-Sim projects, and these are some examples of areas we're considering funding in the future or considering how they could be a part of the picture in the future. So one is reducing the reality gap. By that we mean what happens in the simulation, how similar is it to real life and what would happen in a real world test of the same scenario, and how close do the two have to be to show that the simulation is reliable. Secondly, is encouraging further collaboration in the sector. We believe that's something that has been really successful with the CAV-Sim competition, and we think it's something that is also being encouraged in the Zenzik interoperability project that's ongoing at the moment. So we'd like to continue to encourage this going forward. Next is improving interoperability. So looking, for example, at if we should and if we can standardise how systems communicate with each other, which would also support further collaboration going forward. And then finally, creating a library of defined critical characteristics for use in simulation. So that's trying to come to a common understanding of things like, what do we mean by heavy rain compared to light rain? It could also refer to things like different types of pedestrian or different types of infrastructure, and all having that common understanding of what that should, at a minimum, look like in simulation. So thank you very much for listening. I hope that was interesting. I've included my email on here, so if anyone does have thoughts on anything I've said, but in particular on how simulation can support R&D or safety and security going forward, please get in touch. I think I'm handing over now to Tim Edwards from HORIBA MIRA.
Yeah, thank you very much, Annabelle, and thanks Neil as well for the introductions this morning. So I'm now going to start the presentation of the main VeriCAV project. So hopefully we've got, actually, sorry. Yeah, I shall share my slides then. So yes, I've got the role today of introducing a bit of a technical overview of the project, what it's about, how we've kind of composed the consortium and approached the overall challenges that we're trying to address with the project. So the context really for the VeriCAV project is about progressing towards the deployment of autonomous vehicles. And really, that's about making sure that the vehicles that go onto the road at all levels of ADAS and autonomy are going to be functional and safe and robust through their service. And we recognize that to do that, we need to be able to make a good, strong argument that these products have been well engineered with robust justification that all the test and engineering activities are of a sufficient standard. And verification and validation is going to play a really important role in that. But what we see as an industry is that as the level of autonomy increases, the scope of this verification and validation activity grows ever larger. And the industry is very aware at the moment that simulation is going to be an important mechanism to be able to test this really wide scope in a cost-effective and kind of resource-managed way, and in particular to use scenario-based testing within simulation. So this is, like I say, a well-established situation with the industry, but there's a lot of unanswered questions still about how exactly can we do that? Do we have the tools in place and the processes? And those really are the kind of questions that VeriCAV is seeking to answer. So there's 5 key research questions that I wanted to pull out now at the start of the presentations, and we can come back to these at the end of today's session as well, and just recap on what VeriCAV has done to address them. So the first one really is, how do you actually know which scenarios, which test cases need to be tested for a given system? Given that every system that is developed in a slightly different way and deployed in a slightly different operating environment. Then the question comes of how can we use simulation effectively, and how can we make best use of the resources we have? How do we know that the simulation is going to be a realistic representation of the world the vehicle is going to operate in? A key question, which we feel has been kind of somewhat overlooked in other areas at the moment, is what's the actual acceptable definition of driving you want to see within a given scenario? So if you're generating a very large number of test cases, you need to know what performance you expect in response to every single case, and the balance that you have to achieve between driving to make progress, driving to be safe, and driving to be comfortable and efficient. We also need to think about the fact that we can use simulation to automate large numbers of tests, but actually that in turn is going to generate large amounts of data. And we still need to consider how best to actually automate the process of data analysis and make sure that the engineering and human effort that goes into it is targeted on the areas that need greatest attention. And then finally, there's the question of when can you stop? When do you know you've done enough testing, and how do you make a compelling argument to show that you've done enough testing? So these are 5 really broad and really challenging research questions, and each one of those through the presentations today, you'll see some of the innovative developments that have taken place within VeriCAV. So I'm just going to allow a short video to play now, which gives you probably a better explanation than mine as to some of the background considerations for the project and some of the areas of innovation. So just a couple of minutes of video for you.
Automated vehicles will transform the way we use transport, unlocking time currently spent driving, reducing accidents from human error, and improving mobility for those who can't easily drive themselves. However, automated vehicles need to be tested robustly to ensure their safety before deployment. The complexity and subtleties of driving in a public road environment makes overcoming this hurdle a significant challenge. One increasingly important technique involves testing a range of scenarios in simulation. Testing in simulation allows developers to have full control of test conditions, ease of testing within a safe environment, with the ability to run and repeat large numbers of tests in parallel. The challenge, however, is ensuring realism of the simulation whilst avoiding the need to construct and assess each test scenario manually, which is both time-consuming and costly. This is the challenge VeriCAV addresses. VeriCAV is a framework for simulation-based testing. Automated vehicle developers and test providers can generate and run simulated scenarios with many different combinations of automated vehicle goals, road types, and different behaviour of the other road users. If required, these scenarios can be tailored to the particular automated vehicle that is being tested. Other road users, such as pedestrians and other vehicles, have intelligent behaviour incorporated to react dynamically to traffic and ensure the test is as realistic as possible. We call these smart actors. VeriCAV runs each of these test scenarios in simulation and then applies a range of evaluation metrics to score the suitability and safety of the automated vehicle behaviour, given the specific context of each scenario. Using the latest in AI and search space optimization methods, VeriCAV continuously learns from each set of test results, intelligently selecting the next set of test scenarios to further explore causes of the automated driving failure. This ability to run and evaluate a large number of tests in an automated manner reduces time and cost and provides an efficient mechanism for proving automated driving decision-making. VeriCAV transforms simulation into a highly effective, efficient and powerful tool in accelerating the realisation and deployment of automated vehicle technology. VeriCAV's effectiveness and accuracy has been validated by using cutting-edge facilities, including University of Leeds HORIBA Pedestrian Lab, HORIBA MIRA's Proving Ground, and using Connected Places Catapult's specialised virtual reality driving experience capabilities. Featuring a highly modular framework of testing tools aligned with established industry standards, VeriCAV is designed to ensure both flexibility and compatibility across all simulation and automated driving platforms, both now and in the future. VeriCAV enables virtual simulation to be a significant part of a wider holistic test programme, part of the continued journey to safe, deployable, automated vehicles. VeriCAV is part funded by the Centre for Connected and Autonomous Vehicles via Innovate UK as part of the government's £100 million Intelligent Mobility Fund, supporting the Future of Mobility Grand Challenge. Find out more by visiting our website and visiting our Twitter and LinkedIn pages. VeriCAV, evaluation of automated driving systems using flexible and optimised virtual testing, enhancing real-world automated vehicle safety.
All right, excellent. So yeah, as I say, that video gives you a really nice overview of both the challenges that we're trying to address with VeriCAV and some of those innovative approaches we're taking. So just before I hand over to my colleagues, I can just kind of show you what that looks like in a high level framework for VeriCAV. So the first stage that we talk about is the specification of the actual test scenarios. So a key part of our hypothesis has been that because every system that is being tested is different, different functionality, different implementation, and a different operating environment, we can therefore assume that the conditions that it's going to be sensitive to and the ways in which it might fail are going to be unique to that system. So we want to be able to actually store the attributes of scenarios and generate tests dynamically so that we can actually tailor them for the given test program. When it comes to test execution, we have focused on simulation-based test execution because we know we can automate the coverage of a very large number of test cases. We want to be able to execute those, and to do that, we've been leveraging existing simulation tools. But we have spent a lot of time looking at the interfaces both between our test generator and the actual system under test to make sure that we can be as modular as possible and support as many different test execution platforms as possible. So within the project, our main focus has been on the pre-scan software simulation environment, but making use of established ASAM standards for those interfaces. And similarly for the system and the test, as I say, we want to be able to work with a whole range of different customer applications. But for the sake of the project, we've been using the open source Apollo system, which is a level 4 automated driving system that's freely available. And that's been our kind of reference case. The other thing about a simulation environment, though, is the other actors that you drive with. And the behavior of those other actors is a really important factor in getting a realistic simulation scenario experience. So we've also looked at the enriching of the simulation environment using smart actors, which is something you'll hear more about shortly. But this is all to do with the definition and execution of a test, as much emphasis has been put on the analysis side of the project to make sure that you can interpret those tests in a meaningful way and start to draw conclusions across these large swathes of test data. So the first part of the analysis is with what we call test oracles. So again, this is a concept you'll hear more about in the presentations later, but the concept here is that you can evaluate performance of the vehicle in that particular driving situation. So again, it's giving you a relative score of performance depending on the conditions of each individual test. And then finally, this test oracle data is fed into our search space optimization algorithm, which actually learns from the performance of the system in the test so far to identify the regions in which further testing is required. And that closes the loop, feeding back into further tests. So you get this automated test framework, refining the test cases, learning more about the system over time. So you'll see each individual element of this expanded on by my colleagues in a moment. So the last point that I'm going to make is just to do with the roles and responsibilities within the project. So the consortium here is formed of HORIBA MIRA, and we've been leading on the scenario definition and test analysis activities. We've also developed and integrated the Apollo automated driving system as our case study for the project. We've been working very closely with the Connected Places Catapult, who have been leading the project management and dissemination activities of the project. And they've also been leading in terms of the modular interfaces and system integration and verification validation activities. We're working in partnership with Aimsun, who bring a huge amount of simulation expertise to the project. It gives a really valuable insight into how you can exploit these types of technologies in the future and the challenges with integrating different simulation platforms. And we're also working with the University of Leeds, who are focused on that topic I mentioned a moment ago, to do with smart actors and how you can introduce intelligence into the way different road users respond in a simulated environment. So without any further ado, then I will hand over to the first of the technical presentations, which is William Latham from HORIBA MIRA, who can tell us about the test generation stage. Thank you.
Yes, thank you, Tim. And good morning, everybody. Thank you again for attending today. As Tim says, I'm William Latham. I'm a CAV graduate engineer, and I work for HORIBA MIRA. And today I'll be taking you through test generation. So we're going to cover our approach to test generation. Then we're going to move on to a live demonstration of our test generation web application. And then finally, I'm going to share some hopefully interesting test footage with you all today. So I would imagine that many of you on the call today are familiar with this paradigm of functional, logical, and concrete scenarios. However, for those of you who are perhaps not so familiar or want a bit of a recap, I'll go over that now so that we're all operating on the same page and understand the common terms. So when we want to create a scenario, we start with a functional scenario. And at this point, we're just providing a general description of that scenario. So here I have an example. We have an ego vehicle merging onto a highway, and then a leading actor performs an emergency stop in front of it. Once we have our general description, we're able to move on to a logical scenario where we begin to parameterize that problem and start introducing some logical bounds. So for example, here I've got actor deceleration and event trigger time. And then as you can imagine, the step after this is to create a concrete scenario where we start providing definitive parameter values. So here you can see those same parameters, but now with specific values rather than bounds. Just to help further visualize this, I've included a graph here, and you can see that we have two axes, and each axis represents a parameter. It doesn't really matter what that parameter is, but you could think of it as being an event trigger time or actor deceleration. Between these axes, we have a potentially infinite problem space, which is not very useful. So by introducing our logical bounds, we're able to isolate part of the problem space which is more interesting and is more useful to us. And then, of course, within those bounds, we start to see that we have our concrete scenarios with our definitive values. Okay, so moving next onto our specific test generation workflow. At the beginning of the process, we start by uploading an open drive map. And at the same time, we also include a custom positions file, which includes data such as ego start and stop positions and actor start positions as well. Once we have our open drive file uploaded, we're able to start defining some logical parameters. So these are the logical bounds that build up our logical scenarios. We can then put those logical parameters together and combine them, and then, as I say, start to build our logical scenarios. Once we have those logical scenarios, we're now able to sample that problem space and gain an initial coverage of that problem space. I'm not going to go through analyze and inform at this stage of the presentation because we're going to cover that in more detail a little bit later. So here we have the beginning of our example scenario. And as you can see, it's a relatively simple section of highway with a slip road coming onto it. On the highway, we can see that we have an actor vehicle, and on the slip road that we have our system under test or our ego vehicle. They're both going to progress along their parts of that highway to our first merge zone, where the system under test is going to have to merge in behind the actor vehicle. They will then progress along the highway until they reach the emergency stop zone. At this point, our actor, all things working out, will perform an emergency stop, and we'll get to see how the system under test reacts to that. Okay, so at this point, I'm going to jump out of the slide deck, and technology allowing, I'm going to share with you our web application that we use for generating tests. So I'm going to jump straight in. And as I mentioned before, the first step is to upload an open drive file. So I'll start by selecting an open drive file, and I'll navigate to my resources. See, I have a number of maps available at my disposal. I'm going to pick the motorway map. And as I mentioned previously, we need to associate a positions file with that. Excellent. Okay, so that's uploaded now. And as I say, the next step is to start defining our logical parameters. I've already defined an acceleration and a speed logical parameter, but I'm going to go ahead and upload a simulation time parameter, which we're then going to in turn use in order to indicate to the actor when it should perform its emergency stop. So I'm going to call this sim time. Apologies. And it is going to be of a type trigger value. At this point, I will specify our lower bound. So I'm going to say the minimum time is 17 seconds. And equally, the latest time at which this maneuver could start is going to be at 20 seconds. I'm also going to specify a default value. The logic here is that for some parameters, the user may not want to have variance and instead choose to have a fixed value for every concrete scenario, which is this allows them to do if they so wish. So we move on to the next step, which is creating a logical scenario. I'll give it a really creative name, and I'll insert a duration of 30 seconds. And we can see here that I've already got a road network available, which we just uploaded, and a start position for our ego. You'll notice that we have some configuration settings for smart actors. I'm not going to cover that here, but smart actors will be expanded upon later in the presentation. What I am going to do is add a simple actor. Again, we have the option to choose its start position. I'm going to give it an initial speed of 12.5 meters per second. And then this is where things become a bit more interesting. So I can choose to include a number of different maneuvers. In this case, I'm going to pick a simple one, which is just a speed change. And now I need to associate a trigger with that maneuver. So again, nice and simple. We're going to go with the simulation time condition. So if we progress next, this is where we start to see the power of the solution really starting to come into play now, because I can select our active vehicle and I can bring up all the associated parameters with the maneuvers that we've just selected. So we only selected one, so it's relatively simple, but you can see that we have our speed change maneuver and we have a target speed, which of course is going to be more or less 0 in our case, as it's an emergency stop, an associated acceleration value, and then also for our trigger, we have a simulation time condition. So rather than at this point providing a fixed value, I'm able to look at the logical parameters that we've already configured and added to the database. So here I can pick a target speed, I pick an acceleration. Apologies, I've realized that I didn't properly add the sim time there. It wouldn't be a proper demo if I didn't do something wrong. So yes, apologies. Okay, that's added now. I'll just quickly whiz through this, as we've seen it all before. Oh no. Okay, we got there, we did it, guys. Right, so yeah, as I was, I can now pick logical parameters that we've already inserted to the database. So I'm going to pick the speed, an acceleration, and a sim time. So at this point, I could have multiple, potentially unlimited number of logical parameters to choose from, which really aids the configuration of our logical scenario. I'm going to go ahead and click Use for SSO. And this just means that we're going to use values within those bounds rather than the default value that I talked about previously. We can link that up. And now I can go to test programs. This is just a container for our logical scenarios that I've already set up. And now, see my failed attempts. Now we can generate some concrete scenarios from that logical scenario that we've just set up. So we go ahead. Let's have a look at those. So here we can see that we have some values for each of the parameters that we associated there. And as I click through, you can see that we have quite a nice diversity actually of values for those different bounds. Okay, great. So at this point, we now have 10 concrete scenarios that are ready to be fed in to our simulation environment and start generating some data. So with that, I'm going to take us back to the slide deck. Great. So I've previously run those tests, or tests that are very similar to those, looked at the test data, recorded the footage, and I picked out 2 concrete scenarios that are particularly interesting and show, again, the power of the solution. So here I have 2 videos side by side. This is the first concrete scenario, but I have the 2 different views of the world. So I have the simulation environment view of the world. So this is what pre-scan sees, but I also have the system under test view of the world, which is what Apollo sees. So let's start first with the simulation environment. We can see that the ego is progressing down the slip road onto the highway section where the actor is leading. We can see here that the merge is a relatively easy thing for the ego to achieve in this particular scenario. But then we see that our leading actor performs its emergency brake, and in this case, Apollo decides the most appropriate action is to come to a full stop. So we can watch that same scenario on the right now with our system under tests view of the world. Again, the Apollo vehicle is progressing down the slip road. It's going to look to perform a merge. You'll see its trajectory in a second. And then we see that our simple actor has come to a stop. Apollo has considered its different options and has decided, rightly or wrongly, that the most appropriate action here is to come to a full stop. Okay, I'm going to move on to the next concrete scenario now. And this is more interesting because what you'll see here is exactly the same logical scenario, but just through the variance of those parameters in an automated sense, we're able to see quite a diverse ending to this scenario. So I'll jump straight into it again, starting with the simulation environment view of the world. Again, as before, the ego is progressing quite nicely down the slip road, and we see the actor progressing as well. And we see there quite different behavior. So what has gone on there will probably make a little bit more sense as I show you the Apollo view of the world of this scenario. So we can see that the ego vehicle is proceeding as previously, and we're going to see that it wants to perform its lane change. But there we can see that it's made the conclusion after analysing that particular test that in fact the best option is to retreat back into its lane, effectively abort that lane change, and then ultimately continue on down the highway. So really the takeaway point here, and the important point, is that we've taken two very similar scenarios which were part of a logical scenario, and through relatively small variance in those initial parameters that were automatically generated, we were able to get two very different concrete scenarios in terms of how they ended. And you can imagine that as you would review the performance of Apollo here, you would get two quite different views of the world and hopefully two different conclusions about how it performed. And with that, I'll wrap up and thank you everybody. And I will pass on now to my colleague, Rich Romano.
Good morning, everyone. Thank you for joining. And let me start up my slides. So my name is Richard Romano, and I led the Smart Actors work at the University of Leeds. So the goal of Smart Actors, what we're trying to do is address a major limitation in modeling multi-actor, multi-agent interactions at the small scale, which is that both actors interacting with each other are going to have an impact on what the other vehicle is doing. So if you think of an actor interacting with the Apollo vehicle, as you saw there, you can see that slight changes in what the lead actor did in the merge scenario affected the merging actor, which was the Apollo. So we looked at a wide range of potential new ways of modeling these other actors in the simulation. So cognitive models, machine learning, choice models, and game theory. And then we tested these in a variety of scenarios, pedestrian crossing, right turns, motorway merges, which you just saw, and roundabouts. So I'm going to dive in first with the game theoretic models. So these are basically simple games that were developed by Nash back in the 40s and 50s, looking at how two players can play against each other and try to either come up with typically the best payoff for both of them. So we have our lag car that's merging on the scenario on the motorway, and we have the merging car merging onto the motorway, and the lag car that's opening a gap possibly. And so the question in this particular case is, will you merge with this vehicle or wait? And will the lag car yield or open up a gap or go? And probably all of you have experienced both of these driving as you merge onto the motorway. I'm going to quickly go to the next slide, which is showing this car, vehicle 1, playing a game with vehicle 2 and has decided to merge, and vehicle 2 has decided to let vehicle 1 in, as you can see there. Now, so this is a typical game interacting, but we can go to the next piece. And here, vehicle 6 is thinking about merging with vehicle 2. Vehicle 2 doesn't let vehicle 6 in, but vehicle 10 is let in by vehicle 4. And then you're going to see that vehicle 10 then decides to let in vehicle 6. So there are multiple games that were played there, each to decide which vehicle would merge or not, whether it would vehicle would choose a gap or not. So the important thing compared to some other approaches that have been used to date is this concept of information sharing between the two vehicles. In these cases, both sides know the game and know the rules of the game and completely understand the payoff of the other actor, which might not be the case in the real world. Okay, so just diving in a little deeper, one of the games that I just showed is this dual game where there's a probability that you're going to merge and there's going to be a probability of yielding. So that's kind of showing at the bottom here. And then you can come up with what's called the optimal payoff or the Nash equilibrium for the game, and each vehicle might choose a probability to either yield or not yield or merge. So when we tested a couple different games, another game by Kang and the Liu game from 2007 against GIPS, which is basically just a gap acceptance time model, we tested this and compared it to NG-SIM data that was collected in the real world. I don't have the NG-SIM data on this slide, but essentially we find that these games, these game theory interactions don't work that well when you start to aggregate them. So we looked across conflicts over 10 hours of driving, and we found that these games actually generated more conflicts and way more crashes than in the real world. So in our analysis, definitely these games are interesting, they're very useful, but they need to improve to be used in depth in these types of work. We've also done work with choice models, which is based on a lot of work already done at the University of Leeds. And in these choice models, while we come up with a final gap to pick, that gap is modified by a lot of information. So we've taken real data. In the game theory cases, we just took the parameters that were provided in the literature. But here we actually fit our choice model to the data available. And this data came from a data set in Germany, looking at vehicles going through a roundabout. And we were able to come up with a set of explanatory variables. So the eagle's vehicle speed, the oncoming vehicle speed, and several other options here. So the vehicle size, things like that. And we were able to, again, test this for a range of probabilities. So this is the selection criteria of the choice model. And we were able to find that the choice model is very stable, which is what you want to see. And you can also see that we had 0 crashes and very low conflicts. So actually, we found this model to work very well for the gap acceptance testing within the roundabout. The next one that we did was machine learning models for a motorway merge. Again, we used the NG-SIM data from the US. We've had some data issues with how NG-SIM was collected, and we had to do some data massaging before we could generate the machine learning models. The models themselves are based on long, short memory encoder, decoder, which is based on recurrent neural networks. we pooled a lot of information from all the vehicles surrounding what we call the ego vehicle, and we were able to predict the trajectories of the ego vehicle based on that. Now, one of the things that we added, which is very interesting, is as we learned about, as we trained the model, we actually looked at whether the vehicle in the real world had either maintained speed, decelerated, or accelerated. And we also looked at whether they're maintained their lane or they changed lanes left and right. And we can look at, in each of these cases, how strong the influence of different input parameters were to the decision to make the lane change, etc. And this is the weighting by time to collision of the various vehicles that surround the ego vehicle that helped make the decision in their control. And so you can see that if the vehicle is going to change left, but keep normal speed, that they looked more behind them, and of course to the left of them. And if they're planning to decelerate, they're actually looking both to the front and the back, and mostly in the left lane. And again, same with accelerate. So we found some very interesting information from the machine learning models. We also found that these models could very well predict the future trajectories of the vehicles. So we look at RMS error for each of these machine learning models compared to the actual vehicle motion, and we found very small, so this is in meters squared, root mean squared error. And so actually over time, we found that the errors were quite small, but we still found, actually, one of the challenges with this model is it has a very tough time still doing things like merging and lane changing. The last model that we looked at is our own internal cognitive models that have been, again, developed at the University of Leeds. Based on perceptual decision making, we essentially integrate the information coming to the pedestrian to decide whether it's safe to cross. And these models were developed under a project called Interact, and we were able to find very good fitting of how evidence accumulation models represent crossing decisions. So these are cars approaching the pedestrians deciding to cross, and they're depending on how far away and what speed the vehicle's approaching at. So we fit data to an experiment that was run in our hiker simulator, and depending whether the car is far away or close and how fast it's going and whether it decelerates, we get these very interesting double humps of crossings. And so the actual evidence accumulation models were able to reproduce these double humps very well. And essentially either they're waiting for the vehicle to pass or they're crossing immediately is the main cases for the constant speed. And then the deceleration cases, they're either crossing right away or they're waiting for the vehicle to slow down. So again, here we found the results of our models to work very, very well compared to simulation. I'm going to quickly end it there with just showing, you've already seen the video of Apollo and Prescan interacting with each other, and you can see down in the lower left, we're able to bring in open drive maps and run our models on those open drive maps integrated with Prescan and Apollo. And at this point, I'm going to turn it over to Michael Orgill from HORIBA MIRA, who's going to talk about the test oracle.
Thank you very much, Rich, and hello, everyone. As he's just said, I'm Michael Orgill. I'm a CAV engineer at HORIBA MIRA, and I'm going to be taking you through the next phase of today's showcase. So far, I suppose we've seen the nuts and bolts of what VeriCAV has delivered. We've thought about test generation and how to ensure simulation fidelity and realism with the smart actors. I'm now going to change gear a little bit. I'm going to take all of that great work for granted and say, well, of course, we didn't do the simulations. We haven't generated the tests for the sake of it. We've done them to assess an ADS under test. And actually now we've generated all this data. Let's make an assessment about it. But how do we do that? And that's an extremely non-trivial point. So that's what I'm going to be speaking about. I'm also going to talk about how that process is automated and scaled up, because of course, it's important to appreciate that the whole VeriCAV workflow is only as efficient as its sort of weakest part, as it were, because there's no point in massively automating something like test generation if then the analysis can't keep pace. So that's where we're headed as we go forward. So let's start off by just introducing a bit of standardized vocabulary. VeriCAV views this whole measurement and assessment paradigm through the lens of what we call metrics and oracles. And you can see this broadly as, say, the first layer, what do we measure? And then the oracles are doing the assessment and the judgment. This is where we make a determination about what happened. Down here. Oh, skip ahead before it's ready. So we mean metric in quite a conventional sense. They're functions and statistics of the ground truth. The ground truth, as a reminder, is the raw data you get after a simulation. But we have to acknowledge that that's too vast and too messy to make any determination from. So instead, we need to decide what do we want to extract that we can derive meaning from. So these are the things we measure and measure against, ultimately. And they provide us with indications of the performance by the ADS under test, but also, and this is very important, the context in which the ADS perform that way. We'll come back to this point. Now, oracles, perhaps a slightly less familiar term to those in the audience, but this is where we now make a holistic assessment of the whole scenario. So there's a lot of aggregation here. We go from time series to a single number that describes the whole scenario, and they're derived from these metrics. So we're sort of going down the way here. But oracles also serve a dual purpose insofar that they inform the search space optimization, and we saw that in Tim's opening remarks, and I'll be talking about that in a second section later as well, actually. And just to put that in some perspective, we can see here really we've got the ground truth at the top, which is our sort of simulated version of reality. We need to channel that into some metrics, things we can actually derive meaning from. But at this point, we haven't made any assessment here. When we're on the metrics, all we've done is extract things which we can use to make an assessment. And then our end goal is to arrive here at the oracles where we've channeled our interpretability. But of course, we also have to handle this information loss and blurring. If you think about the amount of time series data here versus what's ultimately a few numbers by the end, there's a lot of channeling going on here. And handling that aggregation is extremely non-trivial and is something which needs to be given careful consideration. Now, so we've identified what we want, and we've identified a framework. We want these oracles at the end, but we have to ask, which metrics should we evaluate, and what oracles should we evaluate? How are we going to make these things that we've conceived of representative? And so one way we can address that is we can say, well, what requirements do we need of the oracles? And so we borrow here a bit of language that's actually quite common in medicine, but totally synonymous with true, false, positive, negatives. And we say, well, okay, on the surface, we need our oracles to be able to distinguish and ultimately penalize through some numerical score poor performance. Now, actually, you think, great, we've generated some metrics. We can look at those and we can just see where they say things were bad, right? That's done. Actually, no, it's not that simple. Because if you think about it, there are moments of transient risk, even when you drive properly and you drive well. You can't escape the fact that it's inherently riskier to be doing a lane change at 70 miles an hour than to be stopped totally still at a red traffic light. the instantaneous risk in those two scenarios is vastly different, even when both are being executed appropriately. You've also got the idea that a automated vehicle may have to respond to someone else's mistake, which may introduce what on the surface looks like poor behavior, but is actually a very good response to someone else's problem. This all derives from the fact that most off-the-shelf metrics we talk about are made for quite general use and in all contexts. So there probably needs to be some refinement there about which metrics are most applicable when. But long story short, we need our oracles to have a high sensitivity. That's the ability to actually detect things we want to detect. But we also need to have high specificity, because if we just look at the metrics, almost every driving scenario is going to have some blip in the metrics. So we need to understand the context in which it happened so that we don't flag things that were totally safe. Otherwise, again, automating and scaling up this process is not viable. So we're trying to land in this top right corner here. Okay, we saw this funnel diagram earlier, and now I want to think a little bit what happens sort of inside this blue box for the oracles. And this now incorporates the ideas that we just introduced. So when we evaluate the oracle, we see it as sort of three-step process, where first we need to go through some sort of scenario decomposition phase. This has potentially two purposes. It could be a simple yes-no, almost, verification that the given scenario transpired. This is actually perhaps overlooked, because when you set a test to be executed in the framework, but the actors are smart and the ADS is intelligent, it's quite possible that all of the players in that scene choose to do something totally different to perhaps what you intended to test. So the test case is not deterministic anymore necessarily from the user's point of view. So it's important that we go through that phase, but we could also use it as a more open-ended feature extraction technique to say, well, what happened in that scenario? And then we can sort of flag certain things. We can then use that information and the metrics to think about sensitivity phase. So this is where we want the sort of worst case scenario. Let's make sure we capture everything we possibly want to capture. But then we go through a final specificity stage where we perhaps rationalize, contextualize, and explain away things that actually weren't as bad as they first looked when we just consulted the metrics a little bit crudely. I wanted to mention just at this point the sort of domains we're talking about when we say oracles. So I've spoken about there being sort of one number. That's sort of one number per category. So we might have a safety oracle, we might have a comfort oracle, might have a progress oracle. There may be more, but these give some notion of the sort of things we're talking about. So we're talking about a small set of numbers by the end. Okay, in the remaining time in my section, I'd like to show you how some of this theory has been delivered in practice. There's lots we could talk about, but the most interesting thing, I think, is this idea of context and our context metrics and how we can use them to achieve this three-step workflow to evaluate an oracle. So now I want you to think about a totally conventional overtake scenario. We have some little images here just to help us visualize that. So the ego approaches the actor from behind in the same lane, indicates and pulls out in perfectly good time, passes a beam of the actor, and then eventually leaves it for dust. Yeah, so this is a totally normal overtake, and I've picked this one because if you watched it played back in simulation with your own eyes, you would say, yeah, that was a good, safe overtake. There was nothing strange about it. So I want you to remember that this is what we're considering a safe scenario. Of course, when scaled up, you can't watch each of them back individually and make this assessment, but this is to sort of correlate automated assessment with a bit of human judgment, right? So that's what we're thinking about here. And then this next figure is quite busy, but let's break it down. So first we have in the background of each of these 6 subplots, a time series trace of our metrics. So this is the middle step in that funnel diagram. And our metrics, for those who are familiar with sort of common metrics in the CAV domain, we've got break threat number, Pegasus criticality score, and steering threat number. these aren't the only three we've used, but they're the three that I've chosen to show here for demonstrative purposes. And if you look at those in isolation, you just look at the time series trace of the metrics. In particular, we see a big spike in the pink and the green. Now, imagine you're now doing an automated assessment of this scenario. So all you see as the oracle step of VeriCAV is two big, scary peaks in the time series data of the metrics. That looks like bad performance. Something there is not working. It's going potentially wrong. So in the sensitivity step, and if that was the only step, this would be flagged as something dangerous, even though we know in this omniscient case that actually this was a safe scenario. So how do we reconcile that? Well, we introduce our context that achieves better specificity. So in the foreground, the bolder lines here, as opposed to the colored lines in the background, we have some probability traces through the time of a scenario for the likely maneuvers of the ego vehicle. And these have been generated using a causal Bayesian network that was inspired by work by Matthias Schreier and his paper about TTCCP, which is another metric, which I won't go into here. Clearly, this gives us massively more information because we can now directly correlate a lane change to the right, which has a big spike in its probability at exactly the same time as the big pink spike in the Pegasus metric. And so through the sensitivity step, this might get flagged as, oh, there was a big peak there in the pink. Maybe we need to look at this again. But actually then, when we incorporate context, and this is interestingly qualitative context as well, right? It's not just numerical. This is a qualitative thing. It is changing lane to the right. We've identified a maneuver. And so we can say, actually, this peak isn't as scary as it looks because it correlates in time exactly with something. And this alludes to a slightly more general point that over time, we expect there to be a sort of, not a formal signaturing process, but that sort of idea where we say, okay, that sort of amplitude peak in Pegasus criticality, when you're also changing lane, that's normal. That sort of amplitude peak when you're not changing lane, that's not normal. And so you see the same blip in the metric. Without context, we can't tell, but with context, we can suddenly make a discernment, and that's really powerful. The other thing to point out is that no metric is going to be perfect, right? We're working with raw ground truth data, turning that into metrics. Some of them are going to have artifacts, and actually this green peak, we could argue is an artifact. That says break threat number peaks, but actually it's at the same time that the car's following the road. So there probably isn't a braking threat. And so you can see how this has another dual purpose to explain away not only acceptable real peaks, but also totally false peaks. Okay, so there was a lot of information there, but hopefully that made some sense and sort of demonstrated how we hypothesize that context can be used. In the closing 30 seconds, I just wanted to show a couple of figures captured from the actual VeriCAV web app. So I've shown figures for demonstrative purposes just a moment ago, but these are from the web app itself. So we can see how you can view time series data of the metrics you've evaluated. And this is totally configurable and interactive with the user. So you can sort of see in as much detail as you want for any concrete scenario that was executed, what the metrics did. And we can also look at sort of parallel axis plot for the various oracles. So again, we said there might be a few oracles, mostly comfort progress. And so we can see how for any one scenario, it's sort of thread through the picture of what its respective oracle scores have done. That's everything that I have to say in this section. And so I'll be back later to talk a bit more, but for now I will hand over to Martin Pett from the CPC, who's going to talk in a bit more detail on the back of this metric oracle stuff about their comfort model and user trial verification. Martin, it's over to you.
Good morning. So, hi, my name's Martin Pett. I work in the Human Insights team at the Connected Places Catapult, and I'm going to talk to you about the comfort model we created as part of the as part of the test oracle and the user trials we conducted to verify the effectiveness of the comfort model. So the task as part of our work package was to develop a comfort model that would be able to test and evaluate how effective autonomous vehicles, autonomous drive systems, ADSs were, and integrate this into the test oracle. So this is one component of the test oracle itself. One of the challenges is that it needs to be based on objective parameters. And as we all are familiar with, comfort is not solely an objective measure, but is physiological, is psychological. And then the other challenge was to do some verification activity using a driver simulator with participants. So defining comfort, writing an algorithm, creating a scoring system that will identify the performance of this model, but also areas to improve, and to create a user trial that mirrored the simulated scenario. So what you've seen so far, if we were to present line drawings of a scenario to participants, that wouldn't be very realistic. So we had to augment those simulations to create a more believable experience. And finally, just to add a bit of fun to the mix, trying to do a user trial during a global pandemic. So we did initially a very large sift of comfort, how comfort is defined, with a subset looking at autonomous vehicle comfort definitions. And as you can see on this diagram to the left here from Cyril Diaz, there are multiple factors that contribute to comfort, many of which are contextual, personal, psychological, etc. And so that's quite a challenge to write a model based on the large variability there is in the population and how they perceive risk and comfort and how they react to different scenarios. So having mapped out quite a large range of parameters to consider, identified the literature which provided objective data with different levels of comfort being defined therein. And we settled on 5 parameters that we felt could be created into a model that would go some way to defining comfort and acting as a base understanding, with the understanding that this would be matured over time and added to. And this graph, this picture here, shows you some kind of visual context as to what the parameters looking at. So the first parameter is acceleration, longitudinal, lateral. The jerk, so the initial push and shove, as change direction or as accelerate. The headway to vehicles in the same lane. The proximity to vehicles passing to the side of you and also overtaking you or coming towards you, sorry. And the gaps needed between vehicles for a vehicle to decide to pull out onto another carriageway from a T-junction or a roundabout. So part of the work here was to normalize and harmonize these different definitions of comfort and between the different parameters make them harmonious. And based on the literature, we had 4 different categories: as comfortable, normal, aggressive, and extremely aggressive. And this was the basis of the model. So, for example, here, when you've got lateral offset, the distance from the side of your vehicle, the ego vehicle, to other vehicles needs to be greater than 0.8 per meter to be comfortable, and the different categories for the different comfort levels therein. One of the interesting relationships to do with acceleration and jerk is that actually, if you're just going straight and accelerating, you have a higher threshold for what you deem as comfortable. But if you accelerate hard whilst turning, then that diminishes. So one of the papers produced this graph here, looking at the relationship between turning, so the lateral and the longitudinal acceleration. So I'll skip forward a little bit here. So we created a scoring system. So having generated the different scenarios, the scoring system was able to look at the different comfort factors here, and starting off at 100 points per 10-second interval. The higher the threshold that was exceeded, the more the negative scoring that was applied. So in this particular scenario, which is a motorway merge, the vehicle at the beginning of the scenario accelerates very aggressively from 0 to 60 in 7 seconds. And that has accumulated a large number of negative scores. resulting in a 0 score here and essentially a test fail. The same scoring process occurs for each of the different parameters. Any score that goes below 60 is a fail, and so that fails the whole scenario. But what's useful about this layout here is that actually this helps autonomous drive system developers to see at what point during a scenario there is a failure that's occurred. So as well as the acceleration at the beginning, as the vehicle gets up to speed, getting ready to join the motorway, you can see here at the end of the scenario, the vehicle comes quite close to the vehicle ahead in the same lane. And I'll come into that in a bit more detail later on, because context is king here. If you are choosing or you're preparing to overtake a vehicle in the slow lane to go into the middle lane, then you will probably accept a lower threshold for that gap as you prepare to indicate and change lane. So in parallel to developing the model, we're also thinking about how we conduct a user trial, how we use as much of the simulation software and data as possible, but also create a believable experience that allows us to test each of these comfort parameters. So plan A was to use our driving simulator with motion actuators. Essentially, this is a motion platform. Allows us to simulate tilt and roll, which gives participants and users a sense of acceleration and how much you're turning and how fast you're going through a corner. The literature also pointed to the need for a wide angle field of view to allow you to use your peripheral vision to detect the rate of acceleration, deceleration, and speed. Unfortunately, small issue of not being able to get into the office because of COVID. So that forced us to pivot our thinking and our technical approach to dealing with running a trial remotely, if that was potentially feasible, the challenges of home working, thinking about sterilizing and health and safety for the participants, logistics, and how we conduct a trial which we would normally do in a lab environment over video conferencing. So in terms of what we had to do to modify the scenarios for the user trial and create a believable environment, we defined 8 scenarios with 4 different maps, created open drive and open scenario files, and then based on those interactions, ran that through FreeScan using Apollo as the ADS, which generated log files. So those log files were both used for the user trial, but also for the comfort model. And as such, we could compare apples with apples. You know, we're testing exactly the same scenario with vehicles moving exactly the same way, but for the user trial, we're adding a bit more believability with line markings, road signs, thinking about the lighting, thinking about trees and environment to make it a believable environment, but not with too much detail that would distract from the task the ADS is performing. And one of the differences we had to do as part of Plan B was to think about how we load these very large, complex simulations onto a headset. So to do that, we actually captured each scenario in the 360 video recorder, and then we built an application that was loaded onto the headset that contains the videos and provided both tutorial videos on how to use VR, because a lot of people hadn't used a VR headset before, and a user interface to allow them to navigate through the different scenarios as prescribed by the trials facilitator. During the trial, we captured data on the headset. So we actually looked at the head orientation to see where they were looking at any point, and that file was captured, allowing us to then replay that later on. And we also asked participants to pull the trigger on the hand controller to indicate at what stage they felt uncomfortable. So that was pulled and released, and that provided a marker in the data. In between each scenario run, we had a standardized questionnaire using SurveyMonkey, which we asked participants to rate each of the comfort parameters. And we also had a data analysis that allowed us to review a data analysis interface tool to be able to look at that data and draw insights from that. So I'm going to quickly show you a video of the user interface and the user experience on the right-hand side there. And on the left, here we have the flattened 360 view video. And in the middle here, we have the graphs showing speed, lateral acceleration, jerk, etc. And here are the scoring metrics that we talked about earlier on. So as you can see, the vehicle accelerates quite harshly to begin with. And so these coloured boundaries show the comfort rating, the normal and the aggressive, and then anything outside that is highly aggressive. So you can see at the beginning of this scenario of acceleration, you're getting a negative 20 score applied here, which steps down. As vehicles pass by in other lanes, you show that the distance between them changes. And this allows us, this is a view of capture from the headset. So just to conclude, so we are still in the early stages of processing and analysing the data, looking at both the objective data captured and the subjective data, and looking at the comfort model versus the participant comfort ratings. We've had some positive, good results and some not so good results. So as predicted, acceleration didn't have particularly good correlation. Participants struggled to really understand how fast they were travelling and how fast they're accelerating and decelerating. So we think that's probably down to the lack of field of view, not having peripheral vision, wide peripheral vision, and not being able to use your peripheral vision to determine how fast you're going, and the lack of haptics and tilts that we're hoping to use with the platform. However, with headway, there was a very positive correlation. So using a visual field of view to look at the rate of deceleration and having a target vehicle in front of you, there was good correlation there. Lateral proximity, again, had positive correlation. Participants generally felt comfortable, but with a caveat that the vehicle's road positioning in lane was consistent, and the lanes were fairly wide on the motorways. So I think we've proven that the data for lateral offset is good, and that people felt comfortable with that, but there's, as with all these things, more work to be done to look at different types of vehicle sizes and road widths and how that affects people's comfort. And finally, the other metric, looking at junctions and the gaps between vehicles and when you choose to merge. There was good correlation with T-junction scenario, where we had a 10-second gap between the vehicles. There's some interesting elements about how comfortable people felt with the approach to the junction in terms of how fast the vehicle decelerated. Did it roll towards the junction, or did it stop and then make a decision? How soon the vehicle decides to pull out after the first vehicle into that gap. But on the roundabout scenario, where we had a gap of 4 seconds, which should have been an aggressive maneuver, not everybody felt that was aggressive, and most people felt quite comfortable with that. So there's a lot of work left to do on this, and I think because humans are infinitely variable and we all have our own mental model and driving style about which we think is comfortable, there's a lot more meat to add to the bones. So unfortunately, I can't give you detailed results because we're still in the process of analysing. But I'd like to say that the report is due out very shortly, hopefully at the very latest, beginning of March. So please keep an eye on the website. I'd like to also say that we've collected a lot more data than we're able to analyse for the trial and beyond the scope of this work. So if there are any interested parties out there who'd like to talk to me and the team about the data we've got, possibly look at doing some analysis of their own and using the software tools we developed, we very much welcome that. And as always, open to future collaborations. Please get in contact. My contact details are on the slide there. So that's my part of the presentation finished. I'm going to hand back to Michael. Thank you very much.
Thank you very much, Martin. And hello again, everyone. I'm back to deliver a second section. And now we're going to be talking about what we have called search space optimization. Now, you'll remember at the start of the presentations today, Tim mentioned this as the last part of the framework, but it's really, really important. And so it's going to hopefully bring together a few of the threads that are sort of open as of this point in the showcase. So without further ado, search space optimization is a bit of a buzzword, I suppose. I think we also heard it in the video at the start. So let's just be clear about what we mean by a search space. So as Will walked us through. Each logical scenario is described by some parameters and their bounds. And there could be any number of those. We saw an example where there were 2 or 3, I think, I can't quite remember, but the point is you could have anything between 1 and a huge number. And so our search space is the parameter space formed by all of those different parameters taken together. So, you could have 2 particular values of 2 parameters, then you could keep one fixed, then change another. You've moved in the search space, you could change both. You've moved to a different point in the search space. And so when there's only 3 or less, of course, we can visualize this. So you can imagine that, an axis for traffic density, actual approach velocity, or precipitation. These are just examples. And of course, once there's more than 3, we can't draw a nice plot for it. But this is what we mean by search spaces. All the different logical parameter ranges laid over one another, as it were. And so what do we mean by optimize that search space? Well, of course, there's an infinite number of different scenarios you could actually execute in that logical parameter space. So we can't do that. So we need to efficiently spend our simulation effort, and that's what the optimization is all about. So first and foremost, optimization needs to demonstrate adequate coverage of the search space. It's no good if there's big gaps where no tests have been executed and where we don't know how the ADS would have performed. But we probably don't need to do a test where a parameter is a fraction of a % different to a previous one, for example. So we're trying to make sure that the search space is adequately covered so that there's no big gaps. I mentioned this just a moment ago, but we need to make efficient use of the simulation effort. It takes a lot of computational power to generate the test, run the test, analyze the tests. So when we're putting all that effort in, we want to be getting maximum return on that expense. We want to use the optimization to try and identify and diagnose regions of poor performance. So the oracles are helping us score and assess that performance, but now we actually need to sort of see how the oracles change as we move around the parameter space and identify, well, where in our logical parameter ranges is something going wrong. So actually relating the poor oracle score, which we maybe spoke about earlier, to, well, what initial conditions produce them. And then at the end of all of this process, we need to quantify our confidence in the performance by the ADS under all the conditions in this scenario. And we mean confidence in a scientific sense there. So how much uncertainty is there associated with the performance? And that's the proxy for that is how much uncertainty is there in the oracle score, amongst other things. Okay, so earlier on in Will's presentation, we saw this workflow. But it was spoken about at that point as sort of open-ended, open loop process. We go through this rigmarole and we can generate from the logical scenarios or concrete scenarios, and that's fantastic. But ultimately, we want the results of a set of scenarios and the oracle scores that come from them to be interpreted in a way that can help us intelligently select the next scenario to execute. So we might initially take a broad sample, and we'll talk about the sort of 3 steps we have in a moment. But then after that, once we've got some initial data, can we use what that's told us to say, okay, I'm interested in this particular region, let's go and investigate there with a higher resolution, so on and so forth. So ultimately, we want to add an extra arrow here that loops this back so we can go around iteratively until we reach some point where we say, okay, we're happy, we've closed the loop, we've explored the space, we've achieved our objectives from the previous slide. Let's close with some statistical arguments. So this is really what we're trying to achieve, this slide here. Okay, so here I'm showing a demonstration again of our hypothesis turned into practice. And this is a 1D example. So you can imagine on the horizontal axis here, there's the logical parameter range, 0 to 8, for example. Doesn't matter what that logical parameter is. And of course, in this case, there's only one, but you can imagine this will extend, right? And then on the vertical axis, we have the oracle score. Now, our first approach is to just take some initial samples. We can't do any intelligent selection until we have at least some reference points. So that's what that first step is all about. And then we use that data to generate an initial surrogate model of the oracle over the search space. So in this example, the red dotted line is the unknowable true behavior. Yeah, so we could never know that, but that's what it is there just to see. And then the blue line is our surrogate model. So this is our prediction of performance for all values of the logical parameter based on the 1, 2, 3, 4, about 8, I think, concrete realizations that we've executed to give us some reference data. Once we've done that, we can then go through a second sort of iterative process which we call confidence mapping, which is basically, let's make our surrogate as accurate as we can. So instead of having these big regions of uncertainty, the blue shaded region, let's execute a test where we're not so certain about performance and reduce that uncertainty and increase our confidence. Now, in the figure on the right, actually, the uncertainty has become very, very small. It probably doesn't need to be as small as it is in this figure. So take that with a pinch of salt, I suppose. But at this point, we've got the first 2 stages. So we've got a high accuracy, confident surrogate model. Now, how do we actually then use this? Well, if we're going to introduce a sort of threshold in our oracles, and exactly where that threshold sits, there's a whole research topic in itself. You know, a bit like we said earlier with the context, that might help set the threshold for a particular oracle score in a particular scenario. So this might be dynamic, but again, for demonstrative purposes, here's a threshold. Now we have our surrogate. We might say, okay, I'm most interested in the transition, where it's just about passing, for want of a better word, and on the transition into failing or dipping below the threshold. So then we can do what we call the exploitation phase, where we sample with high density the regions of interest. Now, the region of interest is up for some debate, but like I say, in this case, we say it's where we're close to the boundary. Interestingly, we're not so bothered about regions where we're very far below the boundary. You know, this test over here on the right, for example, that's well below the threshold. We don't really need to know that it was also very far below the threshold nearby. What we're interested in is that transition point, what's triggering the failure. And so you can then sample as high density as you wish around these regions until you feel you've understood exactly the triggering behavior. So this, in summary, is our 3 steps. Initial sample to give us a reference, confidence mapping to generate the surrogate, and then exploit that surrogate that we've put the effort in to go and spend our computational effort efficiently to investigate really relevant, really informative simulations. Just to close then, I'd like to show, just like I did earlier, some examples from the actual web app. So we can see on the right here a similar example to what I've just shown, but in 2D. So now we have 2 logical parameters along the bottom here, and we have the oracle score in the vertical plane. And you can see how some tests have been executed. That's what the orange dots represent, our concrete realizations. And then we have a surrogate model that tells us what's going on. So we have regions where it's better, regions where it's worse. And then we might go away and sample sort of various contours around these peaks and these troughs. A bit like I said earlier, this can go past 2 logical parameters, but then we can't draw a nice picture because the result's more than 3D, right? So this is as far as we can sort of visualize easily, but it does give us a really clear indication of what's going on and how the search space optimization part of the framework is exploring our parameter space to really maximize VeriCAV's meaning and how much information we can extract from it. That brings to a close my remarks in my second section. So thank you very much for your time in both my sections today. I'll now be handing over to Tom Livermore from the CPC, who's going to discuss VeriCAV's approach to integration. Tom, it's over to you.
Okay, thank you, Michael. Yes, Tom Livermore, a systems engineer at Connected Places Catapult. And as a systems engineer, I'm going to be talking to you about architecture and interfaces. So interfaces are always an area of interest for systems engineers, and particularly important on a collaborative R&D project where you have a complex system that's being developed, as we do in VeriCAV. So there are a few guiding principles that we used to develop the architecture and the interfaces. So these were to be modular, to be flexible, and to use standards where appropriate, but innovate where necessary. So just looking at the modular aspect, the reasons we wanted a modular architecture were threefold, at least. So we wanted to be able to deploy the system ultimately in a distributed manner. So there was, three organizations working on the development of the software, and they were all located remotely. This was kind of exacerbated by the COVID crisis. But ultimately, we wanted a system that could be used in a distributed manner. So that was a key part of the modularity. And also the development. So yeah, there were different teams in different locations, even within the organizations. And a modular framework allowed us to test in isolation, confident that when we came together at integration testing, we would be in a good place to develop the framework further. The modularity also allowed us to develop a flexible solution. And we wanted a flexible solution because this is an area that's developing rapidly. So in three different areas, we were interested in being flexible, at least. So the simulation tool itself, as Tim mentioned, we used Prescan as our simulation tool at the core of the framework. But we're aware that other simulation tools are available. Different users may have different preferences. And ultimately, all of these simulation tools are developing at quite a rapid pace. So we wanted to be able to interchange with as minimal effort as possible if different simulation tools or updates are available. Also, the ADS is obviously a key part we wanted to be flexible about. So yes, again, as Tim mentioned, Apollo was used, but we would want to be flexible in the future. Similarly with actors, so Leeds University were developing their actors and using the interface into the framework. But we would like to be flexible to use other actors in the future as well. And some of those were actually implemented, and I'll give you a quick demonstration of that shortly. So the third guiding principles around standards where appropriate. We, as mentioned, we've used the open scenario and open drive formats that are now being developed by the ASAM organization. And various members of the consortium have been involved in those working groups with ASAM. We're also feeding into the open simulation interface working groups, also by ASAM. And this is an industry kind of wide organization or focus for developing interfaces that allow collaborative work and to tackle this problem in a collaborative manner. So those were the standard interfaces that we were using, but obviously there was innovation required. So particularly around the smart actors, we were keen to develop some additional functionality that wasn't available in off-the-shelf standards. And a lot of work went around the existing standards to develop the functionality that we needed in VeriCAV. So you've seen this architecture diagram previously. So part of the development and the reason we wanted modular and flexible interfaces is that we needed to test each of the elements in isolation before we came together to integration points. So each of these other parties could develop while they didn't have access to the full functionality. And that really proved out the interfaces as well. The interfaces themselves were defined in a single file per interface that was both human readable and machine readable. So rather than having a traditional document that defines the interfaces, this was a single point of truth that could be used both by the software itself, but also the people developing the software to understand those interfaces. So I'm going to focus on the actor interface. So we had 3 different types of potential actor sources. The Leeds University actors you've seen already. We also had an external open scenario engine to run the scenarios that were produced by the test generator. And we also had actors produced in a Unity engine. And the 3 of them both used the same interface, but pointed at different ports and IP addresses, so they could be run separately. So this quick demonstration, you can see that there are a number of vehicles on the right-hand side that are in the pre-scan environment. The green ones are controlled by Open Scenario, and the grey ones are controlled by Unity, and the blue ones are controlled by Leeds University, and they're all available in the pre-scan environment. But on the left-hand side, you can see the world according to the Unity actors.
Okay, apologies. We seem to have had a bit of an issue with the end of Tom Livermore's presentation. And it's unfortunate because it's a really interesting part of the discussion. I'll jump in with the kind of final wrap-up slides, and if Tom's able to come back and finish, we'll do that at the end. So with that in mind, I will share my screen again. Okay, so yeah, we've had lots of interesting presentations. So all I want to do really is do a quick summary and wrap up of the kind of next steps for VeriCAV. But really want to make sure we keep some time because we're getting some very interesting questions from the audience. So in terms of summary, you've seen it a few times now, but really it's this workflow based around automated test generation and automated test analysis in a rich simulation environment is the kind of key essence of what VeriCAV is about. One of the things we recognize is the need to put some initial test specification in place so we can direct and focus test effort. But then it's really about the automated execution within that simulation environment, enriching the simulation with smart actors to give realistic road user behaviors, using a range of oracles to analyze and score performance, and then using that oracle data to inform the regions of the test space which are most relevant and interesting and require further exploration. So yeah, as I say, we've seen elements of all of that, and there are some interesting questions which we hope to get to at the end. So the last thing I just want to add really is a little bit about the future direction. So in terms of the system under test, we've mentioned a few times the fact we've been using the open source Apollo system. And there are a lot of benefits to being able to do that. It's a very advanced and regularly maintained and updated system, but it is something that we don't have the kind of engagement of a developer for, and we don't necessarily have the traceability to the original requirements to be able to show kind of traceable test coverage. So one of the things we're really interested in, I think we see this as an opportunity today, is to reach out and say that with this framework, it'd be really interesting working in partnership with an OEM or ADS developer to go through a fully worked case study for a well-bounded and defined system. And actually, that could be anything from a level 1 ADAS feature all the way up to a level 4 highly automated driving system. So one of the key things about that would be to actually have traceability from the system use cases or formal requirements into the scenarios we use and into the performance targets that we then set on the test oracles. And it would allow us to run the simulation-based evaluation that we've shown today. And then ideally, we'd be interested in repeating that with physical testing to show correlation and validation between the simulation and the real vehicle performance. In terms of the test execution platform, you've seen today results from the pre-scan platform, and I think you would have seen more results from Tom in that final presentation, also in the open source Carla simulation platform as well. One thing we hadn't really had time for today was the discussion around physical testing that we have done within the project. So we did run a series of particularly roundabout and highway scenarios on the HORIBA MIRA proving ground. And actually within that, we were able to generate some more realistic test data and validate some of the test oracle development we've done within the project. But also actually we applied some of these innovative test methods, such as putting intelligent driver models to the different road users into a physical test domain. And we actually had some of our automated target vehicles on the proving ground, adapting their response based on the test conditions as they evolved over time. So that if the vehicle under test makes a different decision, that would then have a consequence on the behavior of those actors. But there's still plenty of scope for further work. And one of the key things is to do with interfaces and standards, which again was part of Tom's discussion really. We're very interested in being able to work with different test execution platforms and to work with different ADS developers. And therefore we see open standards as a really important part of that. So within the project, we've used Open Scenario version 1.0 for our scenario descriptions, which allows us to, for example, work with pre-scan and Carla. But there's a lot of development work going on at the moment with Open Scenario 2.0 and things like the Fortelix MSDL, which give a richer, more flexible way of describing scenarios, which would allow us to do further parameter testing. And I've mentioned, of course, the interest in working with other simulation platforms. So in summary, we've covered many different challenging areas of development within VeriCAV, and each one of those, I feel we've made really interesting progress. I hope you all agree with what you've seen today, but equally, each one of those still has further scope for research and development to take this research even further. So within the test generator, as I mentioned, as we start to use more advanced simulation tools and more advanced interface specifications, we can work with a richer scenario set. There was a question which I answered on the chat earlier to do with map generation. So the principles of test generation and search space optimization can also be extended to automatically generating and varying road network descriptions. And we'd really like to kind of work with that further, again, making use of some new developments in simulation tools to support that. I won't go through the details of all of these, perhaps in the interest of time, just to say that within the simulation environment, there's scope for further modes of smart actor behavior, looking at their motion, further development of additional test oracles, and further extensions and refinement of the search space optimization. So I'll just rattle through that very quickly, because as I say, we only have about 10 minutes remaining, I think, and we're really keen to engage in a discussion with you and take some of your questions. So yeah, thank you to all our presenters, and I'll hand over to Alan Peters at CPC to start the Q&A session.
Excellent, thanks Tim. Yeah, we'll now move on to the Q&A. If I could ask all the presenters to virtually assemble with their cameras on. My name's Alan Peters, I'm from the Connected Places Catapult, I'm part of the VeriCAV team. Excellent, good, we're getting some faces popping up. Some excellent questions all the way through that, sign of the informed audience we've got. And so perhaps if I may, I'll start with one for Michael. So this is one around, what are the metrics used to assess AV safety in simulation? How do these change according to the operational design domain? And can they be carried across to AV safety evaluation in the real world?
Thank you, Alan. Yeah, that's a great question. So metrics which we've used at this point have largely been the sort of, at least coming of age standard ones that are out there in the field. So stuff like brake threat number, steering threat number, Pegasus criticality we saw in the figure that I showed earlier. That's by no means exhaustive. Indeed, we've got the comfort work from the CPC, which is a huge contribution as well. But really, my focus, and I think the project's focus, isn't so much at this point on exactly which metrics. It's more about the hypothesis that ground truth metrics oracles is the right workflow, and this idea that they are probably going to be tweaked or weighted differently according to the ODD is something we totally agree with. Certainly, some metrics are going to be more applicable in certain scenarios, and this is where the context comes in so powerfully as well, right? Because not only does context give you information about the time series trace of a metric you see, it might tell you whether or not it means anything at all, not just, so, you know, it can be used to toggle various things on and off and give you a good level of configurability and intelligence. So hopefully that answers the question.
Can I just add one small comment to that? Because that's obviously focused on the metrics. One thing we've concluded within the life of the project is that actually there probably isn't going to be a single oracle that comes out of this type of analysis. We're looking at evaluating scores of performance in terms of safety and in terms of comfort and the ability to make progress. Those are the things we've shown some evidence of today. But actually going forwards, we're also interested in things like etiquette. So, you know, are you being an aggressive driver? Are you complying with the road safety laws? Are you driving efficiently? So depending on what you're trying to ultimately score as a performance oracle, that's going to inform the metrics that you need to be measuring and evaluating.
Yeah, that's definitely true. And the other part of the question, which I've just remembered that was originally asked, was would they transfer across to physical test? And again, as far as I'm concerned, the answer to that is yes, right? If you can capture the same data from a physical test as you could from the simulation, you can evaluate the same metrics and you can generate the same oracles in theory. So yeah, they're not particularly simulation specific, but I suppose it depends what data you need to be able to capture to generate those figures in the first place. But yes, in theory, you could transfer them.
I think you answered about 3 questions in one there, so perfect. And a follow-on question. The simulated conditions look quite ideal. Is there a way to influence environmental conditions, e.g. friction and visibility, and to then see their influence on the outcome? And would these conditions only be part of the ground truth, or would they also make it into the metrics? So perhaps we start with you, Tim.
Sure, although I'm keen to engage Will and Tom particularly on this topic as well. From my point of view, it comes back to what we've said a few times really about the simulation platforms we're working with. So over time, simulation platforms are getting better and richer in what they can actually simulate effectively. And indeed, a really important part is the models you actually then start to use for the vehicle, for the sensors. So that it's not an area that we've kind of focused our attention on. We're assuming they'll get better. So as long as we can describe the parameters, execute them within the simulation platform and extract them as ground truth afterwards, then in theory, all the methods you've seen today can be applied to that wider set of parameters. As I say, I think Tom and Will might be able to kind of comment specifically on current simulation capability, perhaps.
Yes, so that's part of the reason that we wanted to be flexible in terms of the simulation tool that we were using, because the tools that we were using will update, but also other tools may become kind of more popular. So it really depends on the tool, but it absolutely would be possible.
Excellent. And then perhaps there's been a couple of questions on smart actors, and I know Rich, you've been answering a couple of those in line, but I know you've got a bit to add on there. So particularly the one around the crossing speed of different categories of pedestrians. To what degree have you solved some of those problems in VeriCAV, and what's next?
Yeah. So obviously there's just a bunch of work, maybe not obviously. We are doing a lot of work in this space at the University of Leeds. We have multiple funded projects looking in this space, and we actually have a nice special interest group now at the university across multiple departments, developing models and things like that. There are a lot of challenging questions. I think as I presented a couple of the most recent literature that we've been able to evaluate are very good for fitting models into to data, but not being able to predict new data, which is the real challenge here, and then getting it to be fully interactive. So luckily, our work around cognitive models, we're currently integrating with game theoretic approaches and collecting. We have to collect more data, more information. We have a new associate professor that's doing visual analysis of real world video feeds so that we can understand and look at how vehicles are moving around Leeds and places like that. So we have really a whole tool chain, but it's extremely complex. We want to deliver value continuously, but there's this full interaction that we're looking at, and that's why we're actually doing distributed simulation on another project, looking at the interaction of actors, and we're going to be publishing some papers on that. So human actors interacting with human actors, with the plan to then be able to plug in automated vehicles, which we did in the past with Human Drive, so we can do comparisons of humans interacting with AVs versus other humans, and then developing models. But yeah, it's a multi-year research project, really, or research program, I should say.
Okay, excellent. And then another question that I suspect is another multi-year research question. Another question for Michael on the test metrics. How do you define or quantify adequate when stating that optimization demonstrates adequate space coverage? It's a nice easy one for you.
So in the first instance, we're thinking about adequate coverage as as being measured through the proxy of uncertainty in the surrogate model. So we spoke about how we take the reference data and we try and estimate and predict what happens in the whole search space, but there'll be regions that model also comes with an uncertainty. And so adequate coverage is going to be associated with having a small uncertainty across the entire search space. So that would be my response to that. There may be other measures we come up with in the future, but ultimately that is an objective that we're very confident of. You know, exactly how we achieve it, that may grow and evolve further. Mm-hmm. But at this point, yeah, it's all about the uncertainty in the surrogate. I think Tim had also flagged he wanted to come in on this.
Yeah, I was just going to comment really that clearly there's a lot of work that's been done around coverage-based verification, but it does leave this open question as to whatever kind of fidelity you put on your coverage search. It's always a question of, should you have done more? So I think there's a complement between what we've done here, starting with that coverage-based model, but then building the surrogate model to enhance that. And like Michael says, be able to put some statistical kind of confidence to it. So not only do I have a base level of coverage, but also I've got this kind of good level of understanding of how the system is responding, kind of interpolation between test cases.
Okay. And then a sort of a related but slightly more specific one. Michael, you mentioned in your slides around the particular focus around the pass-fail threshold, and not concentrating on the areas sort of far below or far above. Was there a particular reason for that?
So the particular reason was that we personally saw that as the region of interest, but I wouldn't get caught up on that, as it were. The system, I suppose, is as configurable as it could be. So if as a user, as part of your exploitation phase, that third phase I spoke about, you want to investigate regions really far below the boundary, you can use that. The idea of exploitation is you use the surrogate and what it's telling you to go and look at regions you find interesting. Now, we found interesting the transition, right? Because that tells you where you're going from okay to not okay. And actually failing miserably and failing quite miserably, is there much difference? Well, there may be, in your opinion. That's totally something you can use the system to extract. So no, there wasn't a particular reason is the answer, to be honest. And you could configure it however you wanted to go and exploit what you wanted to do.
Perfect. So perhaps I'll go a little bit future looking and generalize some of the questions. Is there a tangible outcome of the project that could be experienced by sort of interested third parties? And I suppose a related question that we've also had is sort of what's next and how does this scale up? I don't know who wants to come in on that one first.
Well, I guess I was kind of rushing through slightly some of the future directions material at the end here to allow time for this Q&A. So the key messages that I was trying to emphasize really in terms of both the output and the future state of this is that we've kind of demonstrated a proof of concept capability. We've integrated a lot of complex parts together. But we've done it really as that kind of research and development program and using Apollo as our case study. So for me, the most interesting thing is to actually make this a structured exercise next, starting with a defined system. So you put some fixed boundaries, some fixed requirements in, showing how that links through into the scenarios that we test and into the way in which we evaluate performance. So that's definitely the kind of key output. So whilst it's not something that we can just directly make available to people at this point, it's something we'd like to do in partnership with an OEM or ADS developer in that sense.
Yeah, and where do you see the next challenges? You know, there's obviously, I think in the presentations that we were showing, there's a large amount of work that's needed in certain of these areas. Where do we feel that the tricky challenges are likely to be? And perhaps I'll go to Mark Brackstone first for that one.
There's a lot of challenges going forward, Alan, where to start, both in breadth and in depth of what we do. I think one of the USPs of us almost is the fact that we are attempting to address quite a wide variety of challenges with what we've done so far, whereas if you compare us with existing software, they haven't got quite the breadth of what we've done. They've gone into an awful lot of depth on a couple of very important key areas. So there is the question of where do we go next? Do we dive into one or two specific areas to enable us to almost compete with other pieces of software, or do we take forward kind of a development across the board? It rather depends what happens next as to, do we talk to OEMs, what happens with further CCAV funding, etc. There's an awful lot of options out there, so we just really have to see how things develop for us over the next 6 months.
And perhaps a sort of related question is, can some of the learnings and the tools that have been developed over the course of this 2.25 years, can they be used for certification of CAVs as well as the more sort of development and testing purposes as we laid out this morning?
I'd say yes, but we have to see how the entire certification process itself develops in terms of what's actually required by it, because that is a field that's also developing. For example, CCAV project that CPC have got with a life of its own as well. So we kind of have to take it forward and almost in lockstep with what's going on in the field of certification.
Yeah, if I can just add a comment on that, if you don't mind as well. So I think VeriCAV has got this very novel closed loop architecture where we're doing everything in a sequence and feeding back the data we've got and learning and iterating through simulation. So that we feel has a real value, but may not yet be the model that goes into certification. So it's worth emphasizing that each of those individual steps that got us to that point also has a significant contribution to make in isolation as well. So how you sample and generate test scenarios, for example, could be extracted and exploited in other contexts, how you score and evaluate performance, or indeed how you build a surrogate model and evaluate confidence in the testing you've done. Each of those things, and indeed, sorry, Rich, the smart actor behaviors, each of these elements that we've kind of developed can be isolated and exploited as well, and potentially, like I say, add value to certification. Okay, in which case, I think we've reached the end of our time on this Q&A session and indeed the webinar as a whole. I think from my perspective, having worked on this project as well with the team, it's been really fascinating, and I think we've seen a lot of the outputs in the morning today. As such, it's such a complex space, and it's one that really requires a high degree of collaboration, both nationally and internationally.